Consumer chatbots scan the public web for answers. Enterprise AI agents operate differently. They plug directly into a company's private, enclosed network of internal servers. The value of enterprise AI lies in its ability to connect to internal APIs, private databases, and workflow tools, instantly turning siloed data into specific usable answers. This connectivity creates an immediate paradox. To be effective, the agent needs access to everything, which means it technically possesses the power to see everything. Without governance, a junior employee could ask the agent to summarize an unreleased Q4 earnings report or pull a list of executive salaries. This is God mode. Because the agent is unsecured, a low-level request bypasses standard security gates and the human organizational hierarchy to fetch restricted, top-level data. For the developers building these systems, the primary task isn't just writing prompts, it's architecting invisible, fail-safe security checkpoints. The viability of enterprise AI rests on a paradox. Its real-world utility is built on the very restrictions that keep it contained. We can see this in action by tracing a single request. A user submits a prompt, asking the agent to pull a sensitive Q3 contract for a specific client. Unlike a public AI that might hallucinate an answer, the enterprise agent must locate and trigger a specific internal system to find the real document. This is where the Model Context Protocol, or MCP, comes in. MCP is the standardized bridge that dictates how the AI discovers and interacts with internal company tools. The agent uses this protocol to scan available resources, like a private vector database or a specific API, to identify which system can fulfill the prompt. Within milliseconds, the AI identifies the exact downstream server required to fetch the Q3 contract. But the moment the AI attempts to pull that file, it hits an immediate security wall. Locating the right tool is not the same as having permission to use it. These systems are secure by default, meaning they automatically fail closed to block any unverified request. This creates an identity problem. The internal system requires a verified identity to grant access, but the AI agent doesn't have a company ID of its own. Giving the AI a master password or generic service account is a catastrophic risk, granting the software permanent God mode over the entire network. Instead, developers use per-user, permission-aware authentication. They implement OAuth 2.0 flows to verify the specific human behind the prompt. Through a process called token forwarding, the AI borrows the digital ID badge of the specific employee who typed the request. During the session handshake, the AI presents this borrowed token to the upstream system to prove exactly who it is working for. This is the key. The upstream system ignores the AI entirely. It checks only the human employee's permission levels associated with that token. If the employee isn't authorized to see that contract, the request dies. If they are, the connection opens and the data flows. This mechanism enforces the principle of least privilege, ensuring the AI never acts beyond the clearance of the user who called it. While it's easy to build a localized AI prototype, deploying one at scale across an organization requires rigorous architectural discipline. Production-grade systems require zero hard-coded secrets, network-restricted private services, and absolute protection against token leakage. All of these layers, the MCP servers, the OAuth handshakes, and the tool discovery, must execute in milliseconds to keep the user's workflow seamless. Organizations are only willing to deploy autonomous agents because they can trust these invisible underlying guardrails. Ultimately, an AI system's ability to execute business operations is entirely dependent on the structural security that contains it.